Hello my fellow mathletes, today we will solve a few problems using the integration by parts method. Our first problem is integral of e to m tan inverse x divided by 1 plus x squared dot dx. As we can see from this expression, it involves two functions, two main functions, e to m tan inverse of x divided by the second function is 1 over 1 plus x squared. So if we look very closely at this expression and we try to we can see that there exists 1 plus x squared in the exists expression 1 plus x squared. We know that if we take the derivative of d over dx of tan inverse of x, its solution comes out to be 1 over 1 plus x squared. So we can say that the derivative of this tan inverse x exists in this expression. That's one thing. And the second thing is whenever we try to take the derivative of some e raised to the power some function, whenever we try to take the derivative of e raised to the power some function, it will its derivative will simply be d over dx. Its derivative will simply be e raised to the power f of x times d over dx f of x. So by using this expression, we can see that maybe this e to m tan inverse x, its derivative exists here. So if its derivative exists here, then we can very simply solve it by multiplying and dividing by m, which is a constant. So we'll take 1 over m outside. So we can say that this integral can be solved as 1 over m e to power m tan inverse of x plus c. Now if we try to check this solution, it can very easily be checked. Just try to take a derivative of d over dx e to m tan inverse of x divided by m. If we try to take derivative of this, its derivative is very simple. We know that e to the derivative of e to any function is simply e tan inverse x. It's simply this multiplied by derivative of this expression. So d over dx m tan inverse x is simply it's simply 1 over x plus x squared plus 1 multiplied by m multiplied by e to m tan inverse x divided by m. This m will cancel out, leaving us with this expression again. So this solution can be verified both ways. Now that's the solution e of this integral, e to m tan inverse x divided by m plus c. Now the second, I have another problem here, integral of 2x over 1 minus sin x dx. So we will just try to solve it by using, first what I've done here, I've tried to rationalize this expression. By rationalizing, I have multiplied and divided by 1 plus sin x in the numerator and the denominator. In the denominator, it leaves us with 1 plus sin squared x, and in the numerator, it leaves us with 2x plus 2x sin x dx. So this 1 minus sin squared x will become cos squared x, and here I have separated the terms. 2x over cos squared x plus 2x sin x over cos squared x dx. We know that 1 over cos squared x is secant square x, and the sin x over cos squared x will become secant x tan x multiplied by x. So we will try to solve these two expressions by using integration by parts technique. I've taken these two outside and drawn a bracket around it. So for the first expression, the integration by parts method, in the first expression, if we use the integration by parts method of x over x times secant square x dx, it will leave us with the integral of secant square x. We know that integral of secant square x is tangent of x, because if we try to take the derivative of tangent of x, it will leave us with secant square x. So integral of secant square x is tangent of x times x, and integral similarly again integral of secant square x is tangent of x, and derivative of x is 1. So I have not written it here, so it leaves us with integral of tan x dx. And the second expression, x secant x tan x, the integral of this x secant x tan x is secant x, because we know that derivative of secant x is secant x tan x, and the x simply multiplies with it, and in the second term minus sign, and again the integral of secant x tan x is integral of is again secant x, and the derivative of x is 1, which I have not written here. So by simplifying, we can take these two terms on the side, x tan x plus x secant x minus integral of tan x minus integral of secant x. We know that the integral of tan x is equal to secant x, and integral of secant x is equal to secant x plus tan x. If we try to take the derivative of these two terms, it will leave us with the tan x and secant x. So the rest is very simple. X tan x plus x secant x plus log of secant inverse x, because I have taken this minus sign and took it in the power, and this is not a secant inverse function. This is a reciprocal of secant x, and similarly here I've taken it in the power by using the logarithmic properties, because if there is a number being multiplied with the logarithm, we can take it into the power. For example, a log of x is equal to log of x raised to the power a, simply. So that's what I've done here. So again, x tan x plus x secant x is equal to log of cos x, because 1 over secant square x secant x is equal to cos x, and plus log 1 over log secant x plus tan x. So these two terms can be united as log of cos x divided by secant x plus tan x. That's it, and that's the solution.